Hi, we're Team 10, and today we'll be talking about our autonomous guitar tuner, our project for our senior design. Our team consists of 3 senior computer engineers and 2 senior electrical engineering majors. We've used a lot of the skills that we've developed throughout our undergraduate career, such as hardware interfacing, electronics, things of that nature, in order to build this project. The objective for the project was to create an electric guitar tuner where a user can select which string is being tuned, and then as they strum it, they can attach a motor to one of the tuning pegs on the guitar, which will rotate the string until it's tuned. The motivation that we had for choosing this as our project topic was that a lot of the members of our team have an interest in music, and we wanted to figure out a way to introduce some automation to something that's fairly common in music. Because tuning a guitar is something that is fairly common, we thought that'd be a good candidate. Bringing in automation to the process also would allow us to explore those concepts that I mentioned earlier, such as hardware interfacing, motor control, and also some other more advanced topics like frequency detection. The specific goals that we had for this project were to tune the guitar string to within 5 cents of the target frequency. So what's a cent? A cent is just 1% of the difference between 2 notes. So for example, if you're on the E string, it'd be 1% of the difference between an E and an E flat. We integrated wireless communication into our system by having our 2 modules interact wirelessly in order to reduce some of the wiring that's necessary for our system. We also developed a user interface that's simple to use on a laptop for the user to select the string and then visualize a color coding system to view the tuning progress. And in order to make sure that our system was relatively fast, we wanted to ensure that whenever a user started strumming a string, within 10 seconds our system could tune it. Here we have a block diagram overview of the system. We can break it down into 2 subsystems. The first is the motor control subsystem. The motor control subsystem receives a Zigbee wireless signal to an Arduino, and the wireless signal contains the number of degrees that the motor needs to turn. The Arduino then interfaces with the stepper motor using a stepper motor driver in order to actually do the rotation. The frequency detection system is attached to the guitar with a standard guitar audio cable, and after going through a preamplifier, which raises the signal so that it's no longer zero-centered and also increases the dynamic range, it can detect the frequency with an FFT algorithm. It also interfaces with the laptop in order to figure out which string that we need to actually be targeting and also show the user how the process is going. Once we've determined how far off we are in frequency, we use that to calculate the number of degrees that the motor needs to turn, and we send that over wireless. Here you can see what our motor control subsystem looks like in real life. The main brains of this is the Arduino Uno, which is underneath the red XB shield. So the XB module that you see on top of the shield is the particular brain that we used in order to do Zigbee wireless communication. This is what actually receives the amount of degrees that the motor needs to turn. The Uno interfaces with the motor with the stepper motor driver, and the motor driver passes on 12 volts power to the motor that's provided from a computer power supply that's not shown in the photo. The motor attaches to the tuning peg of the guitar with a custom printed tuning peg adapter to ensure a tight fit. Now Denise will explain how our user interface works.
Our user interface is shown in the picture on the left. To start off, the user needs to enter the number of the string they want to tune. Once they've entered the string and pressed the submit button, which is at the bottom of the user interface, the tuning peg of the string that they chose will get filled in with black, as shown in the image. Also, the note of the string that they've chosen will appear in the center. The user interface will then send the string to the Arduino through the serial port. Once that happens, it will wait for the Arduino to send information back once the user has started to strum the guitar. The Arduino will send back either a Y, G, or R, depending on how out of tune the instrument is. If the user interface receives an R, the guitar head will turn red, and then it will continue to wait for another serial input. If it receives a Y, the guitar head will fill in with yellow, and it will also continue to wait for serial input. If the serial gets a G, that means that the guitar is in tune and the guitar head will change to green and then wait for the user to submit a new string. So it will get a Y, G, or R depending on how out of tune the instrument is. If the string is more than 20 cents out of tune, it will receive an R. If it is more than 5 cents out of tune but less than 20 cents, it will receive a Y. And if it is within the 5-cent range, it will receive a G. And now Matt is going to talk about our frequency detection subsystem.
Okay, so I'm going to talk to you about the frequency detection subsystem. Basically what this does is it waits for a serial input from the GUI that Denise was just talking about. Then when it receives that serial input, that will be the string number. When the string number is set, we reset a rolling average and then begin to sample frequencies. And we take that rolling average, we compute an FFT, basically like we're getting the frequencies over this small window of time, finding the major peak, and then that's the frequency that we're using. And then based on the string that was input from the GUI, we're limiting the frequency range that we're actually looking in. That's because when we were actually strumming the guitar, sometimes there's a major peak that is about twice the frequency that we're looking for, and then it settles down. So we don't want that really big frequency to throw us off and to take away from what we're actually looking for, because that can actually throw off our results. So we limit the frequency range, and then we begin to determine the peak frequency value based on which peak we find in that range. If we get 3 peak values within a certain tolerance in a row, then we go to check whether the goal frequency was reached. If it's within 5 cents of the goal frequency, then we are done. We write a G to the serial port, and that gets sent to the GUI. The GUI tells us that we're done, and then we begin looking for serial input again to find the next string. If those 3 peak values in a row are not within 5 cents of the goal frequency, then we go back and we continue on in sampling the frequency. The rolling average continues, and we keep going. This whole time, it's sending information to the motor control subsystem so that as it's checking the frequency, it's being updated and being changed because the motor is turning the pegs and actually changing what we're getting as input. So it's not a never-ending loop, thankfully. The system reliably tunes to within 5 cents of the target frequency. As you can see in this picture, we bought a little clip-on tuner from the Guitar Center just to be able to check our work, just to make sure that it was actually reading correctly. This clip-on tuner actually reads with a tighter resolution of within about 3.7 cents, as our goal was only 5 cents, and yet for most of our strings, a majority of the time we do get within those 3.7 cents. As you can see in this picture shown by the blue bar pointing straight upwards. If that were to go over, there'd be some yellow bars. If it were to go under, it's just the red bars, but we were pretty consistently tuning within those 3.7 cents. Our system also does this pretty quickly, where you're consistently tuning in less than 10 seconds, and our average is actually less than 7 seconds for all of our strings in the time trials that we did. All right, so now Denise is going to tell you about our strengths and weaknesses.
Okay, now for the strengths of our design. The wireless communication between the two subsystems, the motor control subsystem and the frequency detection subsystem, is very reliable. The GUI allows the user to select the string they want to tune and allows them to monitor the progress of the tuning by the changing in colors from red to yellow to green. Also, as we just mentioned, we are very consistent in tuning each string in less than 10 seconds. Some of the weaknesses of our design is that tuning the 2 highest strings tends to take a bit longer because the amplitude of the signals from those 2 strings is lower. It also takes 2 users to tune a guitar with our current design because holding the motor onto the tuning peg and strumming the guitar as one person would be very difficult. Also, our current design is a bit large and clunky, so it would be hard to move from different locations. Now you'll get to see our design in action.
Okay, cool. So here is our GUI. We're going to type in 6 to tell you that we're going to do the low E string. We're going to click submit, and y'all go ahead. Notice how it starts off red, goes up to yellow, and eventually it'll get to green. Right there, there you go, it's tuned. It took a couple seconds. Now we can switch it over to the next string, the 5, and go ahead. Starts off red, it's pretty far away, motor's moving, and there we go, we're tuned. Moving on to the next string, string 4, this is the D string, you go ahead. Starting off red again, yellow, and green. Wow, that's quick. Okay, moving on to the 3, this is the G. All right. There you go, 4 plucks, we're green. Now we go to the 2. It's the B string. It's way out of tune, but it only took 1 turn of the motor to get there. That's crazy. All right, now we're going to the 1 string. It's the high E. You go ahead. This one was far off, but we're good now. Okay. Sweet. That's it. Got all of them tuned. Thanks for watching our demo. This has been Group 10, aka Pawem Tech, with our autonomous guitar tuner.